The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Let me start by basically listing the main things we've learned over the past 3 weeks or so. And I'll add a few complements of information about that, because there's a few small details that I didn't quite clarify and that I should, probably make a bit clearer, especially what happened at the very end of yesterday's class. So here's a list of things that should be on your review sheet for the exam. So the first thing we learned about, the main topic of this unit, is about functions of several variables. So we've learned how to think of functions of 2 or 3 variables in terms of plotting them, in particular, well, not only the graph, but also the contour plot, and how to read a contour plot. And we've learned how to study variations of these functions using partial derivatives. So remember, we've defined the partial of f with respect to some variable, say x, to be the rate of change with respect to x when we hold all the other variables constant. So if you have a function of x and y, this symbol means you differentiate with respect to x, treating y as a constant. And we've learned how to package partial derivatives into a vector, the gradient vector. So for example, if we have a function of 3 variables, that's just the vector whose components are the partial derivatives. And we've seen how to use the gradient vector or the partial derivatives to derive various things, such as approximation formulas. So the change in f when we change x, y, and z slightly is approximately equal to, well, there's several terms. And I can rewrite this in vector form as the gradient dot product, the amount by which the position vector has changed. Okay, so basically what causes f to change is that I'm changing x, y, and z by small amounts, and how sensitive f is to each variable is precisely what the partial derivatives measure. And in particular, we can use, so this approximation is called the tangent plane approximation, because it tells us, in fact, it amounts to identifying the graph of a function with its tangent plane. It means that we assume that the function depends more or less linearly on x, y, z, and if we set these things equal, what we get is actually we are replacing the function by its linear approximation, we're replacing the graph by its tangent plane. Except, of course, we haven't seen the graph of a function of 3 variables, because that would live in 4-dimensional space. So when we think of the graph, that's really with a function of 2 variables. That also tells us how to find tangent planes to level surfaces. So recall that the tangent plane to a surface given by the equation f of x, y, z equals c at a given point can be found by looking first for its normal vector. And we know that the normal vector is actually, well, one normal vector is given by the gradient of a function, because we know that the gradient is actually pointing perpendicularly to the level sets towards higher values of a function. It gives us the direction of fastest increase of a function. Okay. Any questions about these topics? No? Okay. So let me add actually a cultural note to what we've seen so far about partial derivatives and how to use them, which is maybe something I should have mentioned a couple of weeks ago. So why do we like partial derivatives? Well, one obvious reason is we can do all these things. But another reason is that really you need partial derivatives to do physics and to understand much of the world that's around you, because a lot of things actually are governed by what's called partial differential equations. Okay, so that's, if you want, a cultural remark about what this is good for. So a partial differential equation is an equation that involves the partial derivatives of a function. Okay, so you have some function that's unknown that depends on a bunch of variables, and a partial differential equation is some relation between its partial derivatives. So let me see. These are equations involving the partial derivatives of an unknown function. So let me give you an example to see how that works. So for example, the heat equation is one example of a partial differential equation. It's the equation, well, let me write for you the space version of it. It's the equation partial f partial t equals some constant times the sum of the second partials with respect to x, y, and z. So this is an equation where we're trying to solve for a function f that depends actually on 4 variables, x, y, z, and t. And what should you think of, what should you have in mind? Well, this equation governs temperature. So if you think that f of x, y, z, t will be the temperature at a point in space at position x, y, z, and at time t, then this tells you how temperature changes over time. It tells you that at any given point, the rate of change of temperature over time is given by this complicated expression in the partial derivatives in terms of the space coordinates x, y, z. So if you know, for example, the initial distribution of temperature in this room, and if you assume that nothing is generating heat or taking heat away, so if you don't have any air conditioning or heating going on, then it will tell you how the temperature will change over time and eventually stabilize to some final value. Yes? Why do we take the partial derivative twice? Well, that's a question, I'd say it's a question for a physics person, but actually I'm going to, no. In a few weeks, we'll actually see a derivation of where this equation comes from and try to justify it. But really, that's something you will see in a physics class, okay? The reason for that is basically physics of how heat is transported between particles in a fluid, or actually in any medium. But this constant K actually is called the heat conductivity. It tells you how well the heat flows through the material that you're looking at. So anyway, I'm giving it to you just to show you an example of a real-life problem where, in fact, you have to solve one of these things. So now how to solve partial differential equations is not a topic for this class. It's not even a topic for 1803, which is called differential equations without partial, which means there actually you will learn tools to study and solve these equations, but when there's only one variable involved. And you'll see it's already quite hard. And if you want more, then later on we have many fine classes about partial differential equations. But one thing at a time. So just I wanted to point out to you that very often functions that you see in real life satisfy many nice relations between their partial derivatives. Okay, so that was, in case you were wondering why on the syllabus for today it said partial differential equations. Now we've officially covered the topic. That's basically all we need to know about it, okay? But we'll get back to that a bit later. You'll see. Okay. If there's no further questions, let me continue and go back to my list of topics. Oh, sorry, I should have written down. Okay. That this equation is solved by temperature at the point xyz at time t. Okay. And there are actually many other interesting partial differential equations. You will maybe sometime learn about the wave equation that governs how waves propagate in space, about the diffusion equation, which tells you how, when you have maybe a mixture of two fluids, how they somehow mix over time, and so on. There's basically, to every problem you might want to consider, there's a partial differential equation to solve. Okay, anyway, sorry, back to my list of topics. So one important application we've seen of partial derivatives is to try to optimize things, try to solve minimum, maximum problems. So remember that we've introduced the notion of critical points of a function. So a critical point is when all the partial derivatives are 0. And then there are various kinds of critical points. There are maxima, there's minima, but there's also saddle points. And we've seen a method using second derivatives to decide which kind of critical point we have. So I should say that's for a function of two variables to try to decide whether a given critical point is a minimum, a maximum, or a saddle point. And we've also seen that actually that's not enough to find the minimum or the maximum of a function, because the minimum or the maximum could occur on the boundary. So just to give you a small reminder, when you have a function of one variable, if you're trying to find the minimum and the maximum of, say, a function whose graph looks like this, well, you're going to tell me quite obviously that the maximum is this point up here, and that's a point where the first derivative is 0. That's a critical point. And we use the second derivative to see that this critical point is a local maximum. But then, when we are looking for the minimum of a function, well, it's not at a critical point. It's actually here at the boundary of the domain of, the range of values that we are going to consider. So here, the minimum is at the boundary, and the maximum is at a critical point. So similarly, when you have a function of several variables, say of two variables, for example, then the minimum and the maximum will be achieved either at a critical point, and then we can use these methods to find where they are, or somewhere on the boundary of the set of values that are allowed. So it could be that, we actually achieve a minimum by making x and y as small as possible, maybe letting them go to 0 if they had to be positive, or maybe by making them go to infinity. So we have to keep our minds open and look at various possibilities. So we're going to do a problem like that. We're going to go over the practice problem from the practice test to clarify this. So another important cultural application of minimum maximum problems in two variables that we've seen in class is the least squares method to find the best fit line or the best fit anything really to find, when you have a set of data points, what's the best linear approximation through these data points. And here I have some good news for you. While you should definitely know what this is about, it will not be on the test. Okay. Okay. That doesn't mean that you should forget everything we've seen about it, okay? Now, what's next on my list of topics? So we've seen differentials. So remember, the differential of f, by definition, would be this kind of quantity. So at first, it looks just like a new way to package partial derivatives together into some new kind of object. Now, what is this good for? Well, it's a good way to remember approximation formulas. It's a good way to also study how variations in x, y, z relate to variations in f. In particular, we can divide this by variations actually by dx or by dy or by dz in any situation that we want to find, or by d of some other variable, to get chain rules. So the chain rule says, for example, well, there's many different situations, but for example, if x, y, and z depend on some other variable, say, other variables, maybe even u and v, then that means that f becomes a function of u and v. And then we can ask ourselves, how sensitive is f to the value of u? And, well, we can answer that. So the chain rule is something like this. And let me explain to you again where this comes from. So basically, what this quantity means is if we change u and keep v constant, what happens to the value of f? Well, why would the value of f change in the first place when f is just a function of x, y, z and not directly of u? Well, it changes because x, y, and z depend on u. So first we have to figure out how quickly x, y, and z change when we change u. Well, how quickly we do that is precisely partial x, partial u, partial y, partial u, partial z, partial u. These are the rates of change of x, y, z when we change u. And now, when we change x, y, and z, that causes f to change. How much does f change? Well, partial f, partial x tells us how quickly f changes if I just change x. So I get this. That's the change in f caused just by the fact that x changes when u changes. But then y also changes. Y changes at this rate, and that causes f to change at that rate. And z changes as well, and that causes f to change at that rate. And the effects add up together. Does that make sense? OK. And so in particular, we can use the chain rule to do changes of variables. If we have, say, a function defined in terms of polar coordinates r and theta, and we'd like to switch it to rectangular coordinates x and y, then we can use chain rules to relate the partial derivatives. And finally, last but not least, we've seen how to deal with non-independent variables. So when our variables, say, x, y, z, are related by some equation. So one way we can deal with this is to solve for one of the variables and go back to two independent variables. But we can't always do that. Of course, on the exam, you can be sure that I will make sure that you cannot solve for the variable you want to remove, because that would be too easy. So then when we have to keep all of them but handle, take into account this relation, we've seen two useful methods. One of them is to find the minimum or the maximum of a function when the variables are not independent. And that's the method of Lagrange multipliers. So remember, to find the minimum or maximum of a function f subject to the constraint g equals constant, well, we write down equations that say that the gradient of f is actually proportional to the gradient of g. So there's a new variable here, lambda, the multiplier. And so, for example, if fg, well, I guess here I had functions of three variables, so this becomes three equations. F sub x equals lambda g sub x, f sub y equals lambda g sub y, and f sub z equals lambda g sub z. And when we plug in the formulas for f and g, well, we're left with three equations involving the four variables x, y, z, and lambda. What's wrong? Well, we don't have actually four independent variables. We also have this relation g equals, well, whatever the constraint was, relating x, y, and z together. So then we can try to solve this, and depending on situations, it's sometimes easy and sometimes it's very hard or even impossible. So in particular on the test, I haven't decided yet, but it could well be that the problem about Lagrange multipliers will just ask you to write the equations, not to solve them. Okay, so, well, I don't know yet. Okay, I'm not promising anything, but just, before you start solving, check whether the problem asks you to solve them or not. Okay, if it doesn't, then probably you shouldn't. Whoops. Okay. So another topic that we saw just yesterday is constrained partial derivatives. And I guess I have to re-explain a little bit because my guess is that things were not extremely clear at the end of class yesterday. So now we're in the same situation. We have a function, let's say, f of x, y, z, where the variables x, y, and z are not independent, but are constrained by some relation of this form. So some quantity involving x, y, and z is equal to maybe 0 or some other constant. And then what we want to know is what is the rate of change of f with respect to one of the variables, say x or y or z, when I keep the others constant. Well, I can't keep all the others constant because that wouldn't be compatible with this condition. I mean, that would be the usual or so-called formal partial derivative of f ignoring the constraint. To take this into account means that if we vary one variable while keeping another one fixed, then the third one, since it depends on them, must also change somehow. And we must take that into account. So let's say, for example, we want to find, because I'm going to do a different example from yesterday, so that if you really didn't like that one, you don't have to see it again. So let's say that we want to find the partial derivative of f with respect to z, keeping y constant. So what does that mean? That means y is constant, z varies, and x somehow is mysteriously a function of y and z through this equation. And then, of course, because it depends on y, that means x will vary. Sorry, x depends on y and z varies. So now we're asking ourselves, what's the rate of change of f with respect to z in this situation? And so we have two methods to do that. So let me start with the one with differentials, which hopefully you kind of understood yesterday. But if not, here's the second chance. So using differentials means that we'll try to express df in terms of dz in this particular situation. Okay? So what do we know about df in general? Well, we know that df is f sub x dx plus f sub y dy plus partial f partial z dz. That's the general statement. But of course, we're in a special case. We're in a special case where first y is constant. Y is constant means that we can set dy to be 0. Okay? So this goes away and becomes 0. The second thing is actually we don't care about x. We'd like to get rid of x because it's this dependent variable. What we really want to do is express df only in terms of dz. So what we need is to relate dx with dz. Well, to do that, we need to look at how the variables are related. So we need to look at the constraint g. Well, how do we do that? We look at the differential of g. Okay, so dg is g sub x dx plus g sub y dy plus g sub z dz, and that's 0 because we are setting g to always stay constant. So g doesn't change. If g doesn't change, then we have a relation between dx, dy, and dz. Well, in fact, we said we are going to look only at the case where y is constant. So y doesn't change. This becomes 0. Well, now we have our relation between dx and dz. We know how x depends on z. And when we know how x depends on z, we can plug that into here and get how f depends on z. Okay, let's do that. Oh. Uh-oh. Okay. So, well, so again, saying that g cannot change and keeping y constant tells us gx dx plus gz dz is 0, and we'd like to solve for dx in terms of dz. That tells us dx should be minus gz dz divided by gx. Okay, so if you want, this is the rate of change of x with respect to z when we keep y constant. In our terminology, this is partial z, no, this is partial x over partial z with y held constant. Okay, this is the rate of change of x with respect to z. So now when we know that, we are going to plug that into this equation. And that will tell us that df is f sub x times dx. Well, what is dx? dx is now minus gz over gx dz plus fz dz. So that will be minus fx gz over gx plus fz times dz. And so this coefficient here is the rate of change of f with respect to z in the situation we are considering. So this quantity is what we call partial f over partial z with y held constant. That's what we wanted to find. Okay? So now let's see another way to do the same calculation. And then you can choose which one you prefer. So the other method is using the chain rule. Okay, so let's use the chain rule to understand how f depends on z when y is held constant. So let me first write the chain rule brutally, and then we'll try to analyze what's going on. So you can just use the version that I have up there as a template to see what's going on. But I'm going to explain it more carefully again. Okay, so that's the most mechanical and mindless way of writing down the chain rule. I'm just saying here, let's say that I'm varying z, keeping y constant, and I want to know how f changes. Well, f might change because x might change, y might change, and z might change. Now, how quickly does x change? Well, the rate of change of x in this situation is partial x, partial z with y held constant. So if I change x at this rate, then f will change at that rate. Now, y might change. So the rate of change of y would be the rate of change of y with respect to z, holding y constant. Wait a second. If y is held constant, then y doesn't change. So actually, this guy is 0, and you didn't really have to write that term. But I wrote it just to be systematic. Okay? If y had been somehow able to change at a certain rate, then that would have caused f to change at that rate. Of course, if f is held constant, sorry, if y is held constant, then nothing happens here. And finally, well, z is changing at a certain rate. This rate is this one. And that causes f to change at that rate. And then we add the effects together. Okay, see, it's nothing but the good old chain rule. Just I've put these extra subscripts to tell us what is held constant and what isn't. Okay? Now, of course, we can simplify it a bit more, because here, how quickly does z change if I'm changing z? Well, the rate of change of z with respect to itself is just 1. Okay? So in fact, the really mysterious part of this is the one here, which is the rate of change of x with respect to z. And to find that, we have to understand the constraint. Okay? So how can we find the rate of change of x with respect to z? Well, we could use differentials like we did here, but we can also keep using the chain rule. So how can I do that? Well, I can just look at how g would change with respect to z when y is held constant. So I just do the same calculation, but with g instead of f. But before I do it, let's ask ourselves first, what is this equal to? Well, if g is held constant, then when we vary z, keeping y constant and changing x, well, g still doesn't change. It's held constant. So in fact, that should be 0. Okay, but if we just say that, we're not going to get to that. So let's see how we can compute that using the chain rule. Well, the chain rule tells us G changes because X, Y, and Z change. Okay? How does it change because of X? Well, partial G, partial X times the rate of change of X. How does it change because of Y? Well, partial G, partial Y times the rate of change of Y. But of course, if you're smarter than me, then you don't need to actually write this one because Y is held constant. And then there's the rate of change because Z changes. And how quickly Z changes here, of course, is 1. Okay? So out of this, you get that. Well, I'm tired of writing partial G, partial X. So let me just write G sub X times partial X, partial Z, Y constant, plus G sub Z. Okay, and now we found how X depends on Z. Partial X, partial Z with Y held constant is negative G sub Z over G sub X. Now we plug this into that, and we get our answer. I guess it goes all the way up here. Okay. And then we get the answer. I'm not going to, well, I guess I can write it again. So there was partial f partial x times this guy minus g sub z over g sub x plus partial f over partial z. And you can observe that this is exactly the same formula that we had over here. In fact, let's compare these two methods side by side. I claim we did exactly the same thing, just with different notations. See, if you take the differential of f and you divide it by dz in this situation where y is held constant and so on, you get exactly this chain rule up there. Right? That chain rule up there is this guy, df, divided by dz with y held constant. And the term involving dy was replaced by 0 on both sides because we knew actually that y is held constant. Now, the real difficulty in both cases comes from dx. And what we do about dx is we use the constraint. So here we use it by writing dg equals 0. Here we write the chain rule for g. That's the same thing, just divided by dz with y held constant. Okay? So this formula or that formula are the same, just dividing by dz with y held constant. And then in both cases, we used that to solve for dx. And then we plugged into the formula for df to express df dz, or partial f partial z with y held constant. Okay, so the two methods are pretty much the same. Quick poll, who prefers this one? Who prefers that one? Okay, majority vote seems to be for differentials. That doesn't mean that it's better, okay? Both are fine. You can use whichever one you want. But you should give both a try. Okay, any questions? Yes? Sorry, can we use?
Like our directional derivatives.
Yes, thank you. I forgot to mention it. Where did that go? I think I've erased that part. So, yes, we need to know directional derivatives. Okay, pretty much the only thing to remember about them is that df ds in the direction of some unit vector u is just the gradient f dot product with u. So that's, pretty much all we know about them. Any other topics that I forgot to list? No? Yes?
Can you erase free boards at a time?
Can I erase free boards at a time? No, I would need free hands to do that. Okay. let's see. Okay, I think what we should do is look quickly at the practice test. I mean, given the time, you will mostly have to think about it yourselves. But so hopefully you have a copy of the practice exam. Oh, yes. Okay, so let's look at the second. So the first problem is a simple problem. Find the gradient, find an approximation formula. Hopefully you know how to do that. The second problem is one about reading a contour plot. And so before I let you go for the weekend, I want to make sure that you actually know how to read a contour plot. So one thing I should first mention is, this problem asks you to estimate partial derivatives by reading a contour plot. We haven't done that, so that won't be actually on the test. We'll be doing qualitative questions, like what is the sign of a partial derivative? Is it 0, less than 0, more than 0? You don't need to bring a ruler to estimate partial derivatives in the way that this problem asks you to. Okay, I guess. So let's look at problem 2b. So problem 2b is asking you to find a point at which h equals 2200, partial h, partial x equals 0, and partial h, partial y is less than 0. So let's try and see what is going on here. So a point where f equals 2200, well, that should be probably on the level curve that says 2200. So we can actually zoom in. And here's the level 2200. OK? Now I want partial h, partial x to be 0. That means if I change x, keeping y constant, the value of h doesn't change. So which points on the level curve satisfy that property? Yeah, it's the top and the bottom, OK? If you're here, for example, and you move in the x direction, well, you see as you get to there from the left, the height first increases and then decreases. It goes for a maximum at that point. So at that point, the partial derivative is 0 with respect to x. And same here. Now, we're also told, and let's find partial h, partial y less than 0. So that means if we go north, we should go down. Well, which one is it, top or bottom? Top, yes. Here, if you go north, then you go from 2200 down to 2100. So this is where the point is. So now the problem here was also asking you to estimate partial h, partial y, and just if you're curious how you would do that, well, you would try to figure out how long it takes before you reach the next level curve. Okay, and you'd see that, so here, to go from here to here, so to go from q to this new point, say q prime, the change in y, well, you'd have to read the scale, which was up down here, okay? That would be about something like 300. What's the change in height when you go from q to q prime? Well, you go down from 2200 to 2100. That's about, well, that's actually minus 100, exactly. Okay? And so delta h over delta y is about minus 1/3. Well, minus 100 over 300, which is, whoops, I'm getting out of, minus 1/3. And that's the same, I mean, that's an approximation for the partial derivative. Okay? So that's how you would do it. Now, so, okay, let me go back to other things. So if you look at this practice exam, basically, there's a bit of everything, and it's kind of fairly representative of what might happen. on Tuesday. So there will be a mix of easy problems and of harder problems. Expect something about computing gradients, approximations, rates of change. Expect a problem about reading a contour plot. Expect one about a min-max problem, something about Lagrange multipliers, something about the chain rule, and something about constrained partial derivatives. I mean, pretty much all the topics are going to be there.